I know what you're thinking. I came here to learn biology. What the are you doing talking about chemistry? Listen, hear me out. We are essentially made of atoms and molecules way before these form into cells, tissues, organs, and organ systems. Therefore, it is imperative to understand the basis of our own matter. We also take in, excrete, break down, and formulate many chemical reactions in our bodies. From the breakdown of chemical bonds in food to the formation of urine from nitrogenous waste from said food. Any changes to the chemistry of your blood, whether it is iron levels, pH, or glucose, require chemical processes in our bodies to stabilize or maintain homeostasis of our blood. We also get our energy from chemical bonds and in plants. They form those chemical bonds from sunlight, carbon dioxide, and water. The point is, chemistry is essential to biology and thus imperative in understanding the biological processes in the coming videos. All life, in fact, anything, living or non-living, that takes up space and has mass is made up of matter. This matter is composed of elements which are substances that cannot be broken down or transformed chemically into other substances. Thus far, 118 elements have been discovered, but only 92 are found in nature. Of those 92, 30 elements are found in living cells, and of those 30, carbon, hydrogen, nitrogen, and oxygen take up 96% of your own matter. Ready to get started? We must first shrink ourselves to the size of the very units of matter that can't even be seen by a microscope, the atom. In order to do so, we must have special effects. Ready? Whoa!
Oh no. Hello? Hello? Oh no. Can you all see me? Shoot, I must have shrunk myself out of existence. Listen, if you can at least hear me, let's try to continue. What you're seeing here is an atom, and atoms are the smallest unit of an element that retains all of the chemical properties of that element. Carbon is made of carbon atoms, and hydrogen is made of hydrogen atoms. Of course, complex beings such as ourselves are made of combinations of atoms chemically bound together to make molecules. And even more, these molecules make up cells, and so on. Atoms are composed of the following parts. First are positively charged protons, which have a mass of 1 and a charge of +1. Then you have neutrally charged neutrons, which have a mass of 1 and a charge of 0. Both protons and neutrons reside in an atom's nucleus. Finally, negatively charged particles, which have virtually no mass, have a charge of -1. Electrons are located in regions called shells. Each shell has an electron capacity. The first shell holds only 2 electrons, the second can hold up to 8, and the third can hold up to 8. For the purposes of biology, we tend to stop at 3 shells, but higher elements have much, much more. And since atoms make up the 118 elements that exist, Russian chemist Dmitry Mendeleev developed this complicated Tetris piece called the periodic table of elements. In it, he arranged elements into rows and columns based on shared characteristics. For example, the far right column are known as the noble gases, and that the outermost shell has the full set of electrons. For example, helium has 2 electrons in its outermost shell, and argon has 8 in its outermost shell. Because of this, the noble gases are really stable and do not really react to anything because they have all the electrons they need. However, if you go one column to the left, these are called the halogens and are really unstable. That's because the outer shell is missing an electron, meaning that these elements will bond to anything that will give it that last electron, and some results can be disastrous. Let's take a look at hydrogen and helium. Both are gases that are lighter than air, and historically both were used to inflate balloons and blimps. However, hydrogen has 1 electron in its only shell, while helium has 2. Therefore, hydrogen is more reactive while helium is stable. In 1937, the famous Hindenburg blimp disaster occurred, which was an explosion due to being filled with hydrogen gas. So how do you read a block on the periodic table? Well, let's take a look at molybdenum, an element you will probably never hear about again after a while. The large 1 to 2 letter displayed is the atomic symbol. This is the abbreviated Latinized version of the name for hydrogen. The full name of the element is displayed in the language of the reader. The smaller of the two numbers is called the atomic number. This represents the number of protons found in the element. In this case, molybdenum has 42 protons. The larger number of the two is the atomic mass, which is the number of protons and number of neutrons combined. In this case, 95.94. Molybdenum has only 53.94 neutrons, which was solved by taking 95.95, the atomic mass, subtracting the atomic number, 42. Provided that the overall charge of the atom is neutral, the number of protons and number of electrons will be the same. So there is 42 electrons in molybdenum. From there, you can actually build an atom from this information. Let's take a much smaller atom, such as carbon. Carbon has 6 protons, 6 neutrons, and 6 electrons. How do we know this? Well, the proton number is 6 for carbon, so we put 6 protons in the nucleus. 12.011 minus 6 is approximately 6, so that gives us 6 neutrons. And since carbon is neutrally charged, we'll have 6 electrons. The first 2 will be found in the first shell, and then the other 4 will be located in the outermost shell. There are, however, elements of the same type with varying neutron numbers. So while the protons and electrons remain the same, the element has a higher amount of neutrons. These are called isotopes. Carbon-12 is the base isotope for carbon atoms, meaning it has 6 protons, 6 electrons, and 6 neutrons. However, carbon-14 is also seen in nature, including our own bodies. This carbon is made up of 6 protons, 6 electrons, and 8 neutrons. Carbon-14 is a useful isotope to determine the relative age of recently formed fossils, like those of the woolly mammoth over 10,000 years ago. Living things have high levels of carbon-14, but after they die, carbon-14 decays into carbon-12. Thus, the more carbon-12 a fossil has, the older it is. However, carbon-14 is only useful to a point. To figure out the age of dinosaurs or even ancient microbes, you need other radioactive isotopes to help. Elements do not exist alone in nature, but form chemical bonds with other elements. These are called molecules. Molecules form by the interactions of electrons in the shells of atoms. Most atoms are able to form chemical bonds with other atoms. Chemical bonds occur when 2 or more atoms fulfill each other's outer shell electrons. This can be done by transferring electrons from one atom to another, or sharing electrons between 2 atoms. The goal is to ensure that the outermost shell has the entire set of electrons in order for the molecule to have some stability. Remember that shell capacity is 2 for the first shell, 8 for the second, and 8 for the third. In reality, electrons are paired together in these shells, so the first shell has 1 pair, and the second has 4 pairs, and the third has 4 pairs. Let's demonstrate how ammonia forms. Ammonia is made of 1 nitrogen and 3 hydrogens. Using the periodic table, we know that nitrogen has 7 protons and 7 neutrons, both in the nucleus, and 7 electrons. The first 2 are paired in the first shell, and the remaining 5 go into the outer shell. Only 1 pair forms in the outer shell, meaning that 3 electrons are unpaired. Hydrogens have 1 proton and 1 electron with virtually no neutrons. Ammonia forms when the 3 unpaired electrons of nitrogen combine with the unpaired single electrons in hydrogen. Thus, all 4 elements have the full set of electrons in their outermost shell. Hydrogen now has 2, and nitrogen has 8. Before continuing with chemical bonding, we need to bring up ions. Not all atoms have equal numbers of protons and electrons. If they do, they are considered neutral. However, if they don't, then they are ions. Cations are positively charged in that they have more protons than electrons, and anions are negatively charged in that they have more electrons than protons. Oftentimes, chemical bonds occur by transferring the electrons from one atom to another. This is called ionic bonding. One example is good old-fashioned table salt, also known as sodium chloride. Sodium, in its natural form, has 1 more proton than electron, so it's actually missing an electron. Now, chlorine, on the other hand, naturally has 1 more electron than it does protons. However, whenever sodium chloride or table salt forms, The outermost shell of sodium contains 1 electron and the outermost shell of chlorine contains 7. So sodium simply gives up its lone electron, allowing each atom to have 8 electrons in their outer shell, making stable table salt, which has a charge of 0. So while some atoms give an electron to another, others share their electrons. This sharing is called covalent bonding. Covalent bonds are the most common in living things because these bonds affect elements most likely to be found in living things, such as carbon, hydrogen, nitrogen, and oxygen. Ammonia, seen earlier, is an example of a covalent bond in which there's sharing of electrons between the hydrogens and the nitrogens. Water is made up of 2 hydrogens and an oxygen, hence the name H2O. However, hydrogen and oxygen atoms alone are quite unstable. Hydrogen has only 1 electron in its only shell, and oxygen has only 6 electrons in their outer shell. Water is formed by oxygen sharing its 2 unpaired electrons with a single electron on each hydrogen atom. This gives the hydrogens 2 electrons and the oxygen 8. And this is why water is a stable molecule. Of course, sharing electrons is a lot like having friends. And just like friendships, you have some where you feel like the friendship is pretty even and others where you feel like you're doing all the work or maybe your friend is doing all the work. That brings me to nonpolar and polar bonds. Nonpolar covalent bonds happen when the atoms and the molecules equally share the electrons involved. Carbon dioxide and diatomic oxygen are an example. The pool of the electrons from each atom is equal, making the shape of these molecules appear more linear and symmetrical overall. Examples of nonpolar bonds are those seen in carbon dioxide, methane, and oxygen. Polar covalent bonds still share, but do so unevenly, water being an example. This is because the shared electrons spend more time closer to one of the atoms in the bond than the other. The result is a molecular shape that appears bent or asymmetrical overall. In the case of a water molecule, the shared electrons between the hydrogens and oxygen go towards the oxygen end. The result is a partial positive charge on hydrogen and a partial negative charge on the oxygen side. The third type of bond is a hydrogen bond. These are found in polar molecules that try to bind to other polar molecules. In other words, this explains how water molecules bind to other water molecules. Hydrogen bonds are caused by a weak attraction, signified by the dashed lines, between the partial positive charge of hydrogen and the partial negative charge of oxygen on an adjacent molecule. Hydrogen bonds are integral to keeping water a liquid at room temperature. It also explains how water can be easily manipulated at liquid form. Hydrogen bonds are also used to help hold 2 strands of DNA together. This allows the DNA to unwind easily, but also be able to have it put back together. So you hear me discuss water at great length, and in fact, it is so integral to life that I will cover it in our next video, water.